Okay.
Yeah. So I think I have to, that should be lecture 5, but I think I have to finish lecture 3 before. So remind you that lecture 3, what was a causal duality for operas. Okay. Yes. And so the part I have to finish is the third point. So I'm following the same schedule as for causal duality for algebras. So I define the pre-causal duality theory if you want. So I remind you that we gave the definition of all these guys, the bar and the co-bar construction. And we proved this main theorem. So these two theorems that twisting morphisms can be represented by the bar and the co-bar construction. And that the subset of quasi-isomorphism, they are completely characterized by causal morphisms, okay? And let me just remind you that last time, by hand, we tried to solve the operad encoding associative algebras, and we found that this causal-Tate procedure was we have to put one generator per arity, etc., with a certain map which splits these guys into two, okay, and the degree of the generator of arity n was hold on, n minus 2, okay, and let me write d2. d2 of the corolla with n input was a sum for p plus q equals n plus 1, a certain sign that I do not want to make explicit. P, this is the IF leaf, you put the corolla with q, and so I has to live between 1 and p. Okay, so that's where we were, right? So I said that the causal duality theory, so okay, so if you remember what we did for algebras, we started from a quadratic presentation. So we started from quadratic data, right? So say we have an operad P, for instance, as. If we want to resolve P, well, we have the bar-co-bar construction. That's cool, it's functorial, but it's huge. So we want to simplify this resolution. The idea is, well, if we just have P like this, no way. But if P comes with a presentation, yes, we can try to simplify the bar-co-bar resolution. So what is a quadratic data? A quadratic data ER stands for what? So E is an S module, okay? And quadratic means quadratic, that is R should live in some quadratic part. For algebras, R was living in V times 2. So V times 2 is the part of weight 2 of the free algebra on V. We do the same. So R has to live in the part of weight 2 of the free operad in E. Okay? So remember, T of E means 3 is in E. This gives you a representation of the free operad on E. Then 2 is the number of vertices. So you have an example here, Here E is a simple S module, nothing in arity 0, nothing in arity 1. Okay, any arity 2, you have K of that generator. So it's a one-dimensional space in arity 2, okay, and nothing higher up, right? If you take the free operad on E, you get binary trees, planar binary trees, okay? And among planar binary trees, you have only 2 trees with 2 vertices. So this is the quadratic part of the free operad. And well, inside that free operad, you consider just this one-dimensional guy. So this is R. Okay? So this is quadratic. Bon. Do you have any question? That's okay. Quadratic here is the number of vertices. Okay, so from this quadratic data, we can get two things. It's exactly the same thing as last time. So we can construct the associated quadratic operad. Okay. P generated by E with relations in R. Well, so what's that? That's the free operad in E, where you mode out by the ideal generated by R. Okay, so you take all trees labeled by E, and when you see subtrees with R, you kill them. Or you see here, you take any planar binary trees, and each time you see a left comb, you identify it with the right comb. So all the trees get identified, and this guy is one-dimensional in every arity. Okay. Now you do exactly the same thing. Oh, I'm sorry. I'm doing a bad job. Last time I defined this by a universal property. If you remember, this guy was the initial object in a certain category. You define, so for algebras, you define for operad exactly in the same way. So let me remind you, what did we have last time? So we were considering R. R was living in T of E, okay, and I was looking at, say, operad under E, such that that composite is equal to 0. So, okay, and then P.
I think it has nothing to do with you, but with the surround.
I think so, yes. So, okay, you consider the category of operads under T of E such that this vanishes, okay, and the quadratic operad is the initial object of that category, right? And then, if you want to see what it looks like, this gives you an answer to that universal question. Okay, dually, you define the quadratic co-operad, again generated by E and R. You define it by the dual, so here you do some kind of mirror dual. So if I do that, C of E with R should be a sub operad, co-operad of the free co-operad on E. You project that onto, you take guys with two vertices and you kill R. You look at the category of such sub co-operads and you take the terminal object. The terminal object is your quadratic co-operad generated by E and R. Okay. Now we've somehow reached the limit of the analogy. You will see what I mean. Well, here you have this universal question, no problem, going from algebras to operad, you just write sequence, composition, category, whatsoever. And you were able to give a good representation for this guy. But now here, wow, if you remember last time, I gave you a formula, sum of intersection of blah, blah, blah. The same kind of formula holds. You can read it in Grothendieck-Teichmüller's paper, for instance. So it's a sum on vertices of blah, blah, blah. And somehow you take trees where when you focus on any subtree with two vertices, you should see R. So there is a formula based on intersection of, and you should see R somewhere. Please, I don't want to write that. It's impossible to work with such a formula. Okay, for the mind, that's great, it exists, but how do you compute with it? So I will give you another method for computing this. Now, here comes the point. You remember last time we defined the causal dual. The causal dual co-operad associated to the quadratic data. So P anti-shriek is exactly the co-operad generated by the suspension of V with correlators living in the double suspension of R. So what does this mean? This means that you shift the degree of any vector space. So for any arity, you shift it. Okay? E is an S module. Well, actually, it's a graded S module, or you can take a DGS module, but so far I take this only be graded S module. Okay? So you shift, for every arity, you shift it. This is the causal dual cooperad. So, let's see, for instance, if you consider the non-symmetric, this is a non-symmetric example. Okay, so as is given by T of that modulo that. And honestly, please do that exercise of trying to compute, do the exercise of computing as anti-shriek. Well, so in RET2 you will get one element, this is just E, well, S of E. In RT3 you get S2 of R, and please do the exercise of computing the causal dual of as in RT5. You'll get the sum, an alternating sum of 5 terms. Okay, we take all the planar binary trees with 5 leaves and with good sign, and you will get it. And then this exercise is not hard, but so then that I don't know how to compute. Okay, so before to give you the method for computing this, I would like to tell you how we are going to use that exactly in the same way as last time. That is, now we consider the map kappa, which goes from P anti-shriek to P. You see, I want to have a twisting morphism, somehow a very natural one. I'm doing exactly the same thing as last time. P anti-shriek lives in the co-free co-operad on the suspension of E. Let me kill everybody except for the generators. You just desuspend the generators. You get guys in E. With guys in E, they live in the free operad of E. It projects onto P. That's exactly the same formula as last time. You kill everybody except the part of weight 1 that you just desuspend, and you put that inside P. This seems trivial, but the mixture of that with the twisted differential on the composite product gives you a very lovely guy. Okay, now the same lemma. Well, that proposition maybe. By the same computation as we did last time, if we do kappa star kappa, so we take P anti-shriek, we split into 2 parts according to the decomposition map. We apply kappa twice and we multiply in E. Okay? Since these guys only non-trivially applies to weight 1 elements. When we split into 2, only weight 2 guys will give a non-trivial, a possibly non-trivial image. But what is the weight 2 part of P anti-shriek? It's R. So this is 0 everywhere, except for R, which is sent into R in P. This is 0, period. So exactly the same proof. Okay, so equivalently, this means that kappa is a twisting morphism from P anti-shriek to P. So then the idea is to use the general theorem we had last time. Now you see we were trying to resolve P by means of a cobar construction of a cooperad. But what's that cooperad? And what is the morphism between that guy and that guy? I'm telling you right now that if P comes equipped with a quadratic presentation, you have a very natural candidate here, the causal dual cooperad. Okay? So here I'm going to replace all the C by P anti-shriek. Okay. So here and here I'm considering the map, the twisting morphism kappa. Okay, so kappa induces a map from here to here, F kappa, and it induces a map here, G kappa. Okay, so we have a good candidate for a quasi-isomorphism between omega P anti-shriek to P. Now the question remains: is kappa always a causal morphism? No, but in good cases, yes. So let us give a definition to that. Definition. Okay, this is what I would like to write, but mathematically speaking, that's not, say, correct. The operad P is causal if kappa is a causal morphism. Okay, so of course it's not the operad P itself, it's a quadratic presentation of P. So I should not write this, I should write the quadratic presentation. The quadratic data. Okay, but I would always say the opera P, meaning that I have a favorite quadratic presentation in my mind. Okay, and of course the main theorem, the causal criterion is okay. The causal criterion is this last line that you have here. That is, kappa is a causal morphism if and only if the induced map here is a quasi-iso, so you have a resolution. If and only if this map is a quasi-iso. So let me maybe write it once again. The following assertions are equivalent. The first one is the causal complex, say the left causal complex. The second one is the other causal complex. First, this is non-trivial. Okay, this is non-trivial. If you remember, okay, the composite product is not symmetric. So the underlying space of these two guys, they are different. First, then the differential map is defined in a non-symmetric way. So they are different. So these are really two, say, highly non-isomorphic chain complexes. So saying one is acyclic and saying that the other one is acyclic, these are two a priori different statements. Of course, there are assumptions here, weight grading, blah, blah, blah. Okay, and this is equivalent to what? Now, you look at the map F kappa, which is a morphism of DG operad. This is a quasi-isomorphism. Oh. And now, if you look at P anti-Schwick, P anti-Schwick is actually the homology of the bar construction of P. Okay, so that's the main theorem we want to use. So you see the way we are going to use it so far. So this is the main conceptual theorem. The way we are going to use it, we are going to use that what we want is 3. We want to have this nice resolution. Okay, and the way to check that this construction provides us with a resolution is exactly by just computing the homology of this much smaller chain complex. Okay? Okay, so now I think I need to do some kind of applied mathematics. So we'll do applied causal duality theory. I would like to show you on 3 examples how it works. Okay.
So in the algebra case, the causal criterion had this lemma, the comparison lemma.
Yeah, I'm sorry. Yeah, I didn't write proof because I do not have enough space here. You're completely right. The proof follows exactly the same path. Proof, there is first a comparison lemma. So you have a 2 out of 3 lemma. That is, if you're trying to compare two twisted composite products, if you have one map, another one, and the composite of the two, if 2 of these maps are quasi-iso, then so is the third one. The proof is exactly, well, yeah, it's the same, except you have to prove this comparison lemma for operads, or you put your hands into these this composite product. Yeah, it follows exactly the same pattern. Say. Yes. Alors. Okay. So first, okay. First we hear this first guy as anti-Schwick. So far, this is the theory. That's nice, but we are stuck here. We have the definition of that, and we are not even able to compute these elements. So I would like to give you a method for computing the causal dual cooperand. Of course, I will mimic the method we saw last week. So what can we do? Well, we know that each time we had a coalgebra, the linear dual was an algebra. Always. There's no problem of dimension. The same thing holds here. So what we want to do is, what I would like to do is something like that, definition. I would like to define a causal dual operad now. Okay, that should be, okay, the notation we don't care so far. And what I would like to do is I would like to take P anti-Schrick and take its linear dual. What does it mean? For every n you have a vector space and you take the linear dual for every n. That is okay. But actually, well, so I could consider that. That's an operad, that's nice. Well, but you saw last time we had some kind of desuspension here. We put some kind of S. So this is the issue I have to solve right now. Why? Well, let me motivate it like this. This guy, you see, even E is in degree 0 in that example. See, the binary generator of the operad as is concentrated in degree 0, right? But if you consider the causal dual co-operad, now the generator is in degree 1, because it is exactly what you need for the resolution. But if we want to have the causal dual operad now to be back in degree 0, we have to desuspend the generator. Let's say that's what we want. Okay. So to do that, I need to define something, and to define for you a proper, say, suspension or operadic suspension or desuspension. I want to define a good way to suspend or desuspend an operad, not just a chain complex. So for this I need two constructions. The first one is, so there are many tensor products for operads and S modules. This is maybe not the most interesting one, but we need it here. So the Hadamard tensor product, let's say product of two operads P and Q is defined by H stands for Hadamard, can also stand for horizontal. We are going to put, you see, because the composite product, you put guys one above each other. Here you're going to put them one next to each other. So what's that S module? That S module, well, you consider in arity n, Pn, Qn. You just put them one next to each other, okay? And how do you act? Well, by the diagonal action. So that's an operad. You see, if you take pairs and you put them one above each other, you separate them, you compose, and you get a guy in P times Q. So this is an operad. I leave you to check that. This is an operad. So I should not have done this. It answers a universal question. So if you have A, which is a P algebra, and if you take B, a Q algebra, then A times P, this is just the tensor, I mean the classical tensor product of K modules, then this inherits a P times Q algebra structure. Okay, so this construction on the level of operad answers the following question: what's the algebraic structure on the tensor product of two algebras? Well, the operad which acts on that is P tensor Hadamard. Now, this is the first bit of what I need to put here. So I'm going to put the Hadamard product with something. Okay. But then, what I want is the suspension or desuspension operad. So what is the suspension operad? S for suspension. You can look at a very simple operad. You take one-dimensional vector space concentrated in degree 1. So that's the guy we saw last week during the exercise session. So you take a one-dimensional space concentrated in degree 1, and you look at all the multilinear maps from the... So in any n, this guy is one-dimensional. Sure. How many n multilinear maps do you have from n copies of this to this? Just one. Okay. So this is the suspension operad, and I will also consider the desuspension operad. Okay. Which is the same thing, but reversing the degree. Right. Why do we need that? For the following remark. It's not a proposition, but now, following this remark, A is a P algebra if and only if you look at S of A. S of A is S times A. Is A S times Adama P algebra. You see, I'm just applying this to the suspension opera. So each time you have a space and you would like an algebra and you want to understand what is the algebraic structure on its suspension. So you cheat a bit. You have a chain complex and you just want to shift the underlying chain complex. That is not going to destroy the algebra structure, but somehow to shift it homologically in a certain coherent way. That's what you have to do. So this is what we are going to call the suspension of P. Okay, so the suspension of P, the suspension of the operad, is exactly the Hadamard product with that suspension operad. That's a coherent way of suspending operads. Okay. So now, this is exactly what I want to do. So let me think. If I have to put S or S minus 1, in arity 2, for instance, here we have a guy in degree 0. So here we get in arity 2 a guy in degree 1. But when we pass to the linear dual, it becomes an element of degree minus 1. So here I have to put a binary operation in arity 1. So I have to put an S minus 1. Okay. You see? So with this definition now, as Schrick, well, it will have a binary generator. Okay. Do I want to? Okay. And then this guy is concentrated in degree 0. Okay. In P anti-Schrick, we have S here. We have S of that element. But since we take the linear, do you follow? In P anti-Schrick, we have S of E. So we have S of the binary generator. But we take the linear dual. When we take the linear dual of a degree 1 guy, we get a degree minus 1 guy. Okay? And here, what do we have in arity 2? In arity 2 here, we have an operation from S minus 1 to S minus 1. Okay? That's an element of degree 1. The degree of that guy is 1, the degree of the guy is minus 1. So in the end, this is exactly what I denoted by this black or white dotted binary guy, which is of degree 0. Okay? Oh. Before to continue, I would like to say one more word here, because this is exactly what John will need next week. So now at that point, we have to think at the course next week.
How do you invert the box formula?
How do we invert the box formula?
Yeah, the formula in the box.
What does it mean, invert?
It means to find P anti-Schrick as a function of P Schrick.
How do we? Sure, you're right. Let me do it. So say that then I have a proposition which gives me a presentation for this, which is what I'm going to do. Say I have P Schrick. I'm able to fully compute P Schrick. Great. How do you recover P anti-Schrick? You completely dualize that formula. So P anti-Schrick is what? Let me apply the linear dual to that. Okay, so this is given by. Okay. Well, you need these to be somehow finite dimensional in any arity. Okay, for these two to be true. Otherwise, okay. So I need a finite dimensional assumption. But let's forget that a second. Okay. So I take the linear dual of that, and then here, what I should put here is S minus 1 linear dual. Okay. So what is the linear dual of S minus 1? That's S. Okay. And now S, I put it here. Okay. So if I take the linear dual of that, I will get P anti-Schrick times S, and then, so you put again S minus 1 tensor that. So you invert it with somehow the same formula. Okay?
So both S tensor S minus 1 and S composed with S minus 1 or 1.
Yes. Isomorphic 2. Yeah. Yes. Exactly. Just I want to make. Okay. I just want to make one comment about the suspension operad, because we saw that twice during the exercise session. So when are we going to use this kind of device? Not only here, not only say formally here, but you have a very natural operad for which you need that. What is a Gersten-Haber algebra? So if you remember, a Gersten-Haber algebra is a commutative product. Wow. Commutative product, let me see, something like this. So that's a degree 0 commutative product. Okay? And then people say that this should also be equipped with a degree 1 Lie bracket. This means nothing. So here is the definition. So what you have to take a Lie bracket in the suspension ring. Okay, this is a degree 0. Well, when we say commutative product is degree 0, a Lie algebra is a bracket of degree 0. Lie algebra. Lie bracket. Such that blah blah blah. Okay, that's not my goal to say to give the relation. We saw them twice. That's a beautiful definition. Well, it's well defined. Yes, but now say I would like to define the operad which encodes that. Yes, but the operad, you will not say, oh, look guys, this part is going to act on A and that part is going to act on S of A. No. I need to put in my operad, for instance, say I want to write a presentation of that operad. No. I want these generators to both act on A. So the exercise we have to do is to rephrase this. Okay? We have to rephrase that. Okay. So now what we can do, we have to desuspend at the source. So we should get elements from S of A and desuspend at the target. Well, let me denote the induced guy by this kind of bracket. Okay? And what does it change? I leave you to do the exercise that this Lie bracket is Q symmetric. No, this is given. This is not the exercise. Okay. But if you desuspend at the source, you're going to change the symmetry. When you permute S with S, you get a -1. So this is actually a symmetric product. And this one was degree 0, and now this guy is degree 1. That's what people mean by degree 1 Lie bracket. You see, it's confusing. A degree 1 Lie bracket is an operation of degree 1, but symmetric. Okay. Okay, why do I say bracket like this? It's because then I have to translate the Jacobi relation and I have to properly desuspend it to get it here. And then you have signs. So it's not the Jacobi relation, we say plus, it's plus, minus. Okay, such that. Blah, blah. So you see, be very careful. When you want to code operadically Gersten-Haber algebras, you have to put one generator here of degree 0, which should have the trivial representation of the symmetry group. And then you put another generator of degree 1, which has again the trivial representation of the symmetry group. Now I leave John to have a lot of pleasure proving that this guy is actually the homology of the little disk operad. Degree 0, degree 1, no. You will see. You really need that. Okay. In other words, because I promised to use the suspension operad, the Gersten-Haber operad is made up of what? Well, you should have sitting inside the Gersten-Haber operad the operad com, which models the commutative product. right? But then, so this is modeled by Com. Okay, but this guy is modeled by what? So S of A should be a Lie algebra. Okay, so if S of A is a Lie algebra, alors S minus 1 of S of A will be modeled by S minus 1 of Lie. So this is modeled by S minus 1 of Lie. Okay, so inside the Gerstenhaber operad, you should have two sub-operads, Com and the desuspension of Lie. You should have these two guys inside Gerstenhaber. Then there is a theorem, which I have no time to prove today, and since today is the last day for this course, I will not do it. Then you can see that the underlying S module of this operad is you can pull down all the Com guys and pull up all the Lie part. This is called distributive law, but I have no time. Do you see? So already to define, say, one of the key ingredients for deformation theory, we need that suspension or desuspension opera. Okay, now we can do computations of causal dual and causal resolutions. Okay, great. No, I want you. I want to keep that on the board. Not gonna. No. Okay, let me erase that. Okay. So last time we said that we introduced this guy because now we had a quadratic co-operad and we were taking its linear dual. So this should be a quadratic operad. It is, but the presentation will be P of S minus 1 of E star, blah, blah, blah. So let me try to explain you. So proposition. Okay, when E of n is finite dimensional for any n. Okay, that's exactly the same assumption I had last time. The generators of my algebra should be finite dimensional. Then P Schrick has the following presentation. Quadratic presentation. Okay. So you see, if I do not put this part into that business, but by taking the linear dual of the two universal categories which define the quadratic algebra and coalgebra, you can prove that P Schrick is actually given by. Do not write that so far. Okay. I should take E star and modulo some R orthogonal that I have to compute. And actually here I should put an S minus 2. This is without the suspension. Okay. This is a nice operad. It has a beautiful presentation, blah, 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 that we computed last time in the exercise session. Now what is the effect of desuspending? So what is the effect of taking the Hadamard product with that? Well, first, the generator, and let me do the case where E is binary. Otherwise, it's complicated. For free, I will have no example like this. So let's say E is binary. That is, E of n is 0 for n different from 2. And let's say that E2, the result is true, but let me just explain you this example. Okay. So here we have just E2, right? We have just E2. So here actually this is E2. Okay, so we already saw the effect of tensoring with that guy. Now there's no more S minus 1 here. Okay? But now there are, say, two cases. Well, let me do the full case. When E is a symmetric S module and you have an operad. Well, Yes, you took the tensor product with a degree 1 element, so you killed the s minus 1 here. But what is the representation of this? This is a signature representation. So this is a one-dimensional space, but this is the signature of S2. So actually what you have to do here is you have to tensor by the signature of S2. So you are going to twist the generator. Okay? And then believe me, there is a well-defined orthogonal for the space of relations. Said like that, I'm somehow cheating, but I think you believe me. So let me say a few more words about that. So when I said there are two cases, this is the symmetric case, you see. But if I'm working with non-symmetric operad, there's no signature, because I'm not taking into account the action of the symmetric group. So if you're working with non-symmetric operad, you have no such thing. Okay? You remove it for non-symmetric operad. So for non-symmetric operad, you remove it. Okay. Now, how do you compute R orthogonal? Okay, so you compute R orthogonal in the following way. So now for non-symmetric operad and for operad, what? So where is R living? R lives in the quadratic part of the free operad on E, right? Look at the example of us over there. And so R orthogonal should be something which lives in T of E star 2. So I need to define U, a pairing between trees labeled with vertices labeled by E and E star. This is what I am going to do, and this will give you a self-contained proposition. Okay, so what kind of pairing do you consider for in the non-symmetric case? In the non-symmetric case, well, how many trees do you have here? You have the left combs and you have the right combs in the non-symmetric case, right? Modulo some labeling of the vertices, right? Okay. So here I need to define for you a tree pairing. So let's say that. So here, if I take an element of T of E star, so on the left comb, let's call that psi, okay? And if I have another left comb labeled by, say, mu, A and B, so this is an element in T of E star 2, this is an element in T of E 2. Since the two underlying trees are the same, that's good. I put a +1. Okay? And then I will look at the image of A under phi and B under psi. Okay? So if you take a basis for E, the dual basis for E star, you have a complete way of computing this. And then, what about the right combs? You define it exactly by the same formula, except that here now you put a -1. Okay? And of course, when the two underlying trees they do not match, 0. Maybe I should write it. I claim that you have a full method for computing the causation. So now, what is as shriek? As shriek is generated by a degree 1 element. Okay. Should I give name to that? Yes. Let me call that element mu and that mu star. Right? Just apply that formula and forget the signature of S2. I have to put here the linear dual of the generators. Let's say mu star, the dual basis. Now, I have to tell you what is R orthogonal here under that non-degenerate pairing. Well, you have to compute, so in weight 2, the weight 2 part of this guy is dimension 2, and I should take the orthogonal of something which is dimension 1. So this is just one dimensional. So I just need to find for you a non-trivial element in R orthogonal. And what you do that very easy computation. I put what? No, I put star. So you put mu star here, and what should be put on the right hand side because of the signs? Oh no, did I make a mistake? I hope not. I don't know. So what are the non-trivial pairings? You have these two pairings which produces a +1, and you have these two guys which produce a minus plus, but then a minus. Wow! So this guy lives in the orthogonal space, and it generates this orthogonal space. So this guy should be the element that should be put here. So what we proved here is that as is cosul-autodual. Okay? The cosul dual of as is as. Alors, there is something I forgot to tell you last time, and so I should do it here. It's more than a remark, it's a proposition. Why do we call that cosul dual? There is really a duality here. Namely, if you do the cosul dual of an operad, see, you live in an operad, and then you do again the cosul dual, you get the original operad. This is not the same result, right? I applied the cosul dual functor twice. This always holds true. It's really a duality. Okay. Okay, and now I claim that. First, this is the cosul dual operad of as, and we were able to compute it. Now what do you do? Well, now that we have a presentation for that operad, okay, we said that this is as, so now we are able to compute what we have in each arity. Okay, so this is easy. In each arity we have, well, 0, 1, a binary product, a ternary product, etc. Now we are able to compute that. So this is exactly your question. Now we go back here and we take s minus 1 times this cosul dual linear. So now we are able to fully compute all these elements. So nothing in arity 0, the identity in arity 1, one element in arity 2, but it now has the degree 1 because we put the suspension operad here. We have one element in arity 3, it has degree 2, etc. So we have as anti-3. So far we have the underlying space. Look, these are exactly the generators we found last time. Anyway, by hand we computed that, right? And then I claim that this is exactly the causal resolution of as. But you should keep in mind that last time this guy was in degree 0, this guy was in degree 1, etc. So there is a shift of degree, for sure. There is a shift of degree in the Kobar construction. So that's okay. Exactly.
Just a little question. The first one is, did you remove the s minus 1 in the P trick just because you want to simplify things?
It's not simplify. Why? If you want to simplify, yes. I want, for instance, this generator to be of degree 0 if I started from a degree 0 element.
But can you always do that? Can you always remove the s minus 1?
I do what I want. No, I mean, look, no offense. We need some break from time to time. No, look, I say that you somehow force. These guys are very natural and say canonical. But then comes to the point, yes, P anti-Schrick has to be the generators and the Kobar construction of P. But then, how do you compute P anti-Schrick? I said, well, I could take the linear dual of P anti-Schrick. I can. But if I take the linear dual of P anti-Schrick, I will get a presentation with many suspensions and blah, blah, blah. And let's say I want to simplify that.
And the second question is that pairing a little different from the one in the book?
No, that's the same one of the one in the book.
Same? But
Yeah,
in the book you got with plus?
No.
No?
No.
No?
No, no.
Okay.
if I remember well. No, I'm trying to present you the same material.
Okay.
No, I don't want to confuse you. Okay, so far what do we have? The cosidual seems to be the good one. The cobar construction is the guy we have on the left-hand side. Well, what about D2? Being able to compute the underlying guy is okay. But what about the algebraic structure, that is the co-opera structure here, which induces the differential in the resolution? Well, this guy is an opera, okay? So when you compose, you know that when you compose two binary guys, you always get this ternary guy. You know that when you compose this with this, you get an element of degree 6, okay? So each time that I take an element like this, let's say P, Q, and I, each time that I do that in that operad, okay, gamma as shriek or gamma as, this gives me the element of, that's very complicated, 6. Here we have P plus Q minus 1 for any I. So now if we take the linear dual of that map, we'll get the decomposition map. So here what do we have? We take the corolla with P plus Q minus 1. How is it decomposed in that co-operad? That's easy. All these guys gives you that. So dually, this guy splits into the sum of P plus Q equals N plus 1, and for all i's. Oh, that's exactly that formula. Okay. There is one thing I haven't proved. So we computed the underlying space, the CZGs. Great. We have all this. We computed the algebraic structure on the cosidual co-operal. Great. That's exactly the differential. What else? Not a coffee. Is this guy a quasi-isomorphism? Okay. So we need to prove at some point that the cosul complex of as is acyclic. So let us try to see how it works. One second. I will Gerstenab. Now I want to keep Gerstenab. Well, now we can erase that. Okay. So now, what is the causal complex of as anti-free? Well, first, you know, it splits with respect to the arity. So we have a direct sum over n. And here, okay, so what is that guy? Well, you start from so this is one-dimensional linearity, also this, and this is planar. So you take trees with two levels. The top one on the right will be this element. Okay, this is as anti-shriek and this is as. Okay, then what are you going to do to that? If you remember, you are going to take this element, split it into two, okay. So you are going to split that into two in all possible ways. Then, to that element, you apply kappa. So if it's binary, you view it in as, and if it's not binary, 0. So you take the sum of all possible ways of pulling up a binary corolla. Okay? And then this guy, you multiply it in as. So in the end, you get something like this. Okay? So this is as anti-shriek, and this here is as. Okay, do you see what you do? You have n, and now here you get n minus 1, and you have the sum for all i's between 1 and n minus 1. Well, there is something I will not explain, is all the signs. So here you have a lot of signs and blah 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 because of the suspension. Okay. Yeah. Okay, and so on and so forth. And then you continue, and then you pull up binary corollas like this. Okay, so in general, what do you have here? You have something like this. Oh. The number of corollas should match. Alors 5, wow. Let me see something like that. Okay, so here you have a certain k, and here you have I1 to ik. Okay, and what is the top term? The top term is when you have pulled everything up. Okay, that is n here and nothing there. This is the chain complex that you have to prove that it is acyclic. Okay, so I leave you to prove that actually this chain complex is the chain complex associated to the augmented n-2 simplex. You take the cellular complex associated to the n-2 simplex, and you get exactly that chain complex. Therefore, since this is contractible, this guy is acyclic. Okay, that's quite easy to see. Okay, so we proved now that A cis causul with that quadratic presentation. We prove that A cis causul. Therefore, this map is a quasi-isomorphism. Wow. So we work during, I don't know, 6 hours just to find back that example. Cool. Okay. Let's go to more, say, non-trivial examples. Alors, let me tell you what I have in mind. I will do Lie, Com, and then Gerstenhaber. And then, when we arrive to Gerstenhaber, you will leave the room because it's very complicated. Ima and Andy know what I'm saying.
Could you state the proposition at the top of the middle blackboard?
Sorry?
You started writing a proposition and then you changed it. And what's this?
Alors, you want to know where the proposition finishes?
Yeah, so you
Yes!
wrote it in the binary case. Could you give the statement?
Actually, it's finished here.
Oh, okay.
You see, if you take E to be binary, finite dimensional, then P3 can be computed by that formula. But somehow this is not precise. What's our orthogonal? For which pairing? For that pairing. So if you consider that pairing on trees with 2 vertices, you have an orthogonal space which is well defined, and it's that guy. And I gave you an example. Yes.
That's the 2 questions. That's the non-symmetric version.
Yes, I'm going to do the symmetric version now.
Another question. There are, in the literature,
Yeah.
2 sign conventions
Yes.
for A infinity.
Yes.
Now, I don't want to know which signs you have here. I want to know if you have. So this is a completely formal way of getting one convention.
Yeah.
Do you have a way of getting the other convention?
Yeah. But so far I explained no sign here.
No.
1 second.
But you would have a sign if you.
Yeah. Yeah. Yes. It all comes from the following point. I chose left minus right comp. Choose right minus left. Because then you change the orientation of the first associahedra. This will force to change all these and you get the other sign convention. The starting point is here. What kind of basis somehow I took for the space of relations. Okay. Symmetric case. Now, if you look, say that we want to understand Koncevich and Tamarkin, not all the papers, but the ones on deformation quantization of Poisson manifold, I need to do, say, a symmetric example, and I need to do the example of Lie, because Lie algebras, in deformation theory, we have Lie algebras which model deformation problems. We look at more Cartan guys, and then we have to play with L infinity algebra and infinity morphism this afternoon. But first, I would like to give the definition of what is a resolution for Lie. So again, I could do that by hand. That's not that hard. I could do it by hand, but I prefer to show you on an example. So here, what do we have? We take the 3 symmetric operads on one generator, and here it's skew symmetric. So this actually is the signature representation of S2, put in degree 0. Okay. Let me remove the mu. Then, what is the Jacobi relation? Let me write it like this. Okay. Lie Schrick is an S so far. Blah blah blah. This is true. Okay. Then how do I compute Lie Schrick? Okay, so I need to give an analog of that proposition above for symmetric operads. Okay, so now we have the signature representation here, and I need to define you another pairing. Okay. So now I'm going to use the following bases for that. So I have to take somehow a three bases, but they're symmetric. So I'm going to use the following three bases. If you give me trees in space, I have only three of them with two vertices in binary. Namely, I have to choose what are the inputs. They are in space, right? And then you label the vertices by elements of E, etc. Okay? So I need to define a pairing on these three guys. So first, if the two trees they do not match, if you have one tree and another one, whatever the labeling you have here, this is 0, okay, if they do not match, if the underlying trees are different. Okay? And when the two trees are the same, you take plus. Okay, for any of these trees, for the trees which are the same, you put plus everywhere. Okay, so it's always plus plus. Is that okay? So here is the proposition. You can compute the causal dual operad by this method. Let us see what it looks like. So what it looks like for Lie. Okay, right. So let me remove this. Dot means the linear dual of the bracket. Okay, so what do we have for Lie now? So for Lie, it is generated by one-dimensional guy. So the dimension of T of that is equal, in RET 3, or in way 2, it is the same. This is 3. How many different labeled trees do you have in RET 3 or in way 2, which is the same? 3. 1, 2, 3, 3, 1, 2, 2, 1, 3. How many relations do I have? I have 1. So the orthogonal should be of dimension 2. Okay. Now let me give you two different guys in this orthogonal space. You compute. I will do one. Okay. You take the difference of 2. And then if you compute that, that's very easy. This guy is 0, 0, plus 1. This guy is 0, 0, so plus 1, there is a minus, it's minus 1. Okay? So the difference of any two guys of T of E star gives you an element of our orthogonal, then it's dimension 2. So what I have to put here is this element. Sorry. For instance, and I don't know, 1, 2, 3 minus 3, 1, 2. Okay. Right? Let us interpret that. That's the brute computation. Okay. We started from an element, so this is E, and E2 was the signature representation of the symmetry group, S2, in degree 0. What is now signature of S2, E2 dual? So here, what do we have? Is degree 0, there's no problem. The linear dual of the signature is again the signature, but then we twist it with the signature. So now this is the trivial representation. Okay? So what is an algebra over that? That's a binary product which is commutative. Right? And then, what does this, oh, sorry. What's that relation for a commutative product? This relation, look.
Isn't that 0?
Isn't that 0? Yeah, that's 0. But what is an algebra over that? That's a space equipped with that, such that this is 0. So this is equal to that.
It's 0 in the quotient, but I mean, you can change 2 and 1, or how many things?
Yes, they are in space.
So then they are already 0 before the quotient.
They are? No, I don't see why it should be 0. This is a commutative operation. They are symmetric. This, let me do it. Give me one second. Oh, sorry. Sorry. This is what? Yeah, sure. Of course. These are cyclic permutations. Of course. Stupid. Of course. Sure. But what does it mean? You see, so now if you have mu, this if you call that mu, then what does this mean? It means that mu of A1, A2, mu of A3 is equal to. But then, I won't write it here, I will use the commutativity of that. So I will rewrite that 3 like this. Oh, and so what you have is this is A1, mu of A2, A3. So this operad is nothing but the operad which encodes commutative algebras. So we've proved that the causal dual of Lie is calm. And this conceptually explains the constructions of Quillen in rational homotopy theory. Alors, Quillen was using Lie algebras and co-commutative coalgebras, and you see that the causal dual of an operad should be a co-operad. The causal dual of Lie should be co-com. Here I cheated, I wanted to compute the causal dual operad. Okay? But here, Lie anti-Schrick is what? Is com. So this models co-commutative coalgebras. And then in Quillen's paper, you have bar-co-bar constructions where he introduces some suspension. So when he takes a Lie algebra, he considers the co-free coalgebra on the suspension of. Oh, for sure. Period. And in the other way around, because I said that it's causal it's dual functor, then what you have by the same computation, you have that if you compute the causal dual of com, you get Lie, which is a duality which appears in Sullivan's paper. So now, so what is Lie anti-Schrick? I think I will do it this afternoon, but just to tell you. So now, what are the generators that you should put to resolve Lie? You should put 1 per arity, because com is easy. It's the same story now. Okay, you have 1 per arity, except that it is always the trivial representation of the symmetry group. The product is the same. Okay, the coproduct is different. Now, here I have to be careful at something. Here, I mean, if I have 1, 3, 4, 7. Oh, can I do 7? No, I can't do 7. 6, 2, and 5. I get 1 from 6. Okay, so here I have to be careful at the labelings, right? So let me do it slowly. The causal dual of Lie is com. Good. Com is 1-dimensional per arity. How many commutative operations do you have? 1. What is the product here? If you give me 2 products, it gives you the associated product in the corresponding arity. Now, if you dualize that, what is Lie anti-Schrick? The underlying space is, you take linear dual of that, the dimension is the same. You just shift the degrees, Oh, but be careful, here you have now signs. This is endomorphism of S minus 1. So here, this was completely symmetric. Here, each time you have the signature. So here you have signature of S2, signature of S3, etc. What is the degree? 1, 2, blah, blah, blah. So we have here the full space of the CZGs for the resolution of Lie. Well, if it works, it will work. Okay. See, these are the good space of generators. You see, I didn't compute them one by one. By means of causality theory, I produced all of them like this, under a universal property. Then, what is delta? Well, you have to take the sum of 2 like this, with all the possible labelings. So, maybe I can have... Well, you see, it's a bit stupid. These guys are completely commutative. So I could do something like that. I could put them at the first place, okay? I could put them at the first place, just, it's completely symmetric. And then I have to choose elements here, and I have to choose elements there. Voila. One second. Okay? And these, well, they could be, for instance, the shuffles. So this is exactly the sum over all PQ shuffles, and here I labeled by my shuffle sigma. Okay, except that here it's a right module, so I have to take the inverse of shuffles, that is unshuffles. But that's okay. So here is the decomposition map of Lie anti-Schwick. And so I think I want to keep that formula for this afternoon, because then I will give you the definition of an L-infinity algebra, and it will be based on that formula. Okay. So far, you have the generators, CZGs for Lie, you have the boundary map, but I did not prove that the map is a quasi-isomorphism. So I should prove that the causal complex is acyclic. So let's look at the causal complex. Okay. No, this is stupid. Okay, let us try to unfold a bit. So what's that? That is S minus 1 Hadamard product of, let me put it in the other way around. Hold on. Okay. Okay. So it is that S module. But let me look. I mean, this is a Schur functor. The Schur functor is completely characterized by the image on some vector space. Let me look at that. What's the meaning of that? The meaning of that is, you take Lie of V. This is the free Lie algebra. Okay? Now, you take the free Lie algebra, and the effect of looking at that is you suspend that Lie algebra, and you take the co-free, co-commutative coalgebra on that. Okay? So this suspension corresponds to that. I'm going a bit fast. I would like you to trust me. And then I take the linear dual of com of that. That is the co-commutative coalgebra. Co-free, the free co-commutative coalgebra. Or you want to see co-free. There are too many coco here, but this is free co-commutative coalgebra. Okay? So this is the underlying space. Co-free, polynomials on the suspension of the free Lie algebra. And then the boundary map extracts something here, the binary guy here, and applies it here. What's that? You extract some binary guy here, and you multiply two elements for Lie. This is exactly the Cheval-Eilenberg chain complex of the free Lie algebra. Which is acyclic. So we prove that the operad Lie and the operad com, they are causal. So we have two operads which are causal. Alors, do we still? Yes. Do you have any question?
Is that S on V or outside?
No. It's S of. Oh, I might make a mistake. There might be an S minus 1 here, but I'm sorry. This is maybe a D. This is maybe something like that. The chain complex is acyclic, or any of its suspension or this suspension acyclic. I don't care. So my memory cannot record that. So. These are easy cases.
A probably naive question. Does this have anything to do with Poincaré-Berkoff-Fit or not at all?
Yes, sure. In the proof of that,
You have
yeah.
somewhere?
Yeah.
Just in the proof of that?
Yeah.
Nothing more?
Yeah, you know, Poincaré-Berkoff-Fit,
We didn't
I'm
learn
not
it.
crazy of Poincaré-Berkoff-Fit for the following reason. We saw last time that this map of operads were completely giving the universal enveloping algebra of a Lie algebra. And then when you want a basis, but here I'm somehow not working with basis, so far. Okay, and then let us conclude with lecture 3 right now. Okay, what about Gerstenhaber? It's a lovely guy, right? So now if you read Tamarkin, you would like to do Gerstenhaber algebras up to Homotopy. Woo! Alors, you will have some time during your lunch. So I propose you that you put Gerstenhaber here, blah blah blah, the presentation, and you try to find by hands the space of CZGs. Try 5 minutes, no more, please. Okay, so I hope that you agree that this is not possible. It's not mathematically speaking. I mean, my brain is too short, and maybe yours. Okay, so first the by hand method, the causality method for you. Well, now there are two guys, Ezra and John, and they said, well, look, we have causality theory. Well, so let's write a paper on that and try to do the causal dual. Okay, so let me tell you, you take Gerstenhaber and you compute, so this is their result, you compute the causal dual of Gerstenhaber. Well, what's beautiful is that this is Gerstenhaber again, up to some suspension. Okay, so why? Let me try to explain you why this result. Here, please accept that Gerstenhaber has this shape. Not Gerstenhaber, the opera Gerstenhaber. Murray Gerstenhaber is in very good shape. Please. Okay. Now, well, you know that the causal dual of COM, well, under the causal dual functor, these two guys, COM will give you Lie, right? So COM will give you Lie, okay? And Lie will give you COM. This is the causal dual functor. I'm trying to explain you, and of course I'm cheating a lot, so I hope you won't ask me the proof. Well, in the exercise session, why not? So, COM will give Lie, Lie will give COM, right? Yeah, but there is this nasty S minus 1 here, okay? So actually what you have is S there, right? And then, what am I writing? And I said that this should be S minus 1 off. Yeah. And now, if you do, once again, COM should give Lie, this is true. Lie should give COM, this is true. The causal dual of S minus 1 is S, okay. So that should be Schrick. Yes, and this is S of, sorry. Okay, here is the result. So it's somehow causal autodual up to suspension. You see?
Sorry, when you say you've been cheating, is it true that it behaves well with respect to
Perfect.
composition?
Sure. I mean,
That's true.
All I said is true. I'm cheating just
No, but
all the
generally,
time.
with respect to composition, the causal dual
I
behaves
never defined the composition here. I'm just talking about the underlying guys. I never told you the operatic composition. Let me show you why. What does it mean? What does it mean that the operatic composition here, when you have guys, those underlying spaces like that? I want a map from here to here. This means that I want a map from okay. Of course, the circle product is associative. So then what I need somehow a way to twist these two guys. I don't see. So then you have what we call a distributive law. which tells you exactly how you twist these two guys. Somehow it is a way to pull up Lie guys and pull down the Com guys. So this is what I haven't explained you. And then, wow, cool. Now Coms guys are next to each other and Lie guys are next to each other. So here, yes, you can apply the composition in Com, and you can apply the composition in S minus 1 over E. You see? Bon. So already in your paper there are computations like this, and then with ND and IMA we tried even further to, so we tried to completely describe that. Wow, what did we use? Blah 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 shuffles, extended shuffle. Well, anyway, this is too complicated for me. Okay, so I hope you won't need all the details. But sorry. Then this method by distributive law allows you to prove that this guy is causal. So Gerstenhaber is a lovely opera, though not that simple. Okay. Okay, so here is the end of lecture 3. Now I would like to present you one method. We have 10 minutes, maybe. I won't go long, but okay. You see, the operatic guys will tell you the following: how complicated does this get? Why Ascom and Lie were they simple? One generator. Why is Gerstenhaber extremely hard? 2 generators. It gets exponentially hard with the number of generators. So the difficulty is, if you keep that in mind, okay. Now think at BV, for instance, the operad of BV algebras. Well, exponential 3. You have 3 generators. Okay, so you have all the presentation. Now there is a simple way for proving that an operad is causal by means of what people in computer science call rewriting methods. So this is what I really would like to present you, because I hope you will leave this room less afraid. And with this method you can handle the case of BV, of Gerstenhaber, and so on and so forth. So this is what I would like to explain you. That you should view this somehow as a break. There's no math. I'm going to explain you a method. I mean, I will hide all the math, the proofs, under the carpet. They are beautiful, but we have no time for that. Okay, so we can begin lecture 4. That's my fault. So, well, let's just put it rewriting method. Okay. So, case 1, associative algebras. I will just give one example. So I should do the Kono algebra, the holonomy Kono algebra, but this is not the one I prepared, but I'm sure it applies to it. So example, you consider the following quadratic algebra, that is polynomials in V, and polynomials in V are what? Well, they admit the following quadratic presentation as an associative algebra. Okay. So I want a method to prove that this guy is causal. This algebra is causal. Of course, second will be non-symmetric operad, and third will be symmetric operads. We are going step by step, right? Okay. So step 1. Choose a basis. Oh, sorry. A totally ordered basis. For V. Well, let's say that here, look, in my example, let's say that here V is as dimension 3, okay? And of course I choose that x1 is less than x2 is less than x3. Don't want to be confusing. Okay, so step 1 is that. Right. Now we consider the lexicographic order on words in letters in view of it. We consider the lexicographic order on words with letters in that. Okay? Let me see how I code the steps. Too much with the book. Oh, sorry, this was step 2. Okay. Alors, I can consider the lexicographic order, but why the lexicographic order? The one I need is I would like to have a good order on words, such that when I concatenate them, this map is increasing. That's the property I want. So you can take any other order which satisfies this property. I consider this one. Okay? Now, since, so for instance here, what you have x1, which is less than x2, which is less than x3, which is less than x1, which is less than, and blah, blah, blah. Okay? Well, you know the lexicographic order. Right? Now that we have an order, we had an order on the basis. So now we have an order on the three.
Sorry, this is not the lexicographical order.
Really? Why?
Well, at least in the dictionary, the words,
Yes.
any word beginning with A will appear before any word beginning with Z.
I have to take the area.
Sure. No, I want length and then. I don't care anyway.
Don't write it.
No. We have to be precise. Give me a second. Actually, I don't care. I want to compare. Let me finish this. I want to compare. I need here only to compare words of the same length. Then words of different lengths, I don't care. So, you of course, think you're right. But let's say that, let me vague, and let's say, oh, I know that this is true. I know that this is true. I don't want to compare. Okay. No, you're right. Completely right.
Should we call it graded lexicographic?
Yeah, sure. Okay, graded lexicographic. Okay. Okay. Oh no, wait. Is it still in step 2? Yes. Now, okay. You have first the generators. We have an ordered basis. Now we're considering the relation. So we want an order which will allow you to compare guys with 2 letters so far. Then we choose a basis for the space of relations. Okay. So here I will have x1 times x2 minus x2 times x1, x1 times x3 minus x3 times x1, x1, x2. Oh, I'm writing them in the wrong anyway. Okay. So you choose a basis. Now there is a way to choose a clever basis. Or there's a clever way to choose a good basis. This is right, this is a k-linear basis of the space of relations. Okay. But now we have a good order on these guys, right? So, for instance, this is bigger than that one. Sorry. Okay, so these elements, they are always greater than these ones, in the way I wrote them. So I want to choose a basis such that the first term here is always what we call a leading term. That is greater than all the other ones. Actually, what I want is a 1 here, 1, 1, 1. And I want that, by playing with several relations, I want that there is no leading term up here. So what is a leading term? A leading term is the biggest term of a relation. I consider this set. Here I have 3. And I want to see no leading terms here. You see, I could take the sum of these two. It's again a relation, right? And I could make a basis with the sum of these two, this one and that one, right? So now I want no leading term here. in this case, it's very easy. It's not 1, which is equal to sum of several. It's 1, this is equal to that, this is equal to that, this is equal to that. But you could have more, you will see later. Okay, step 3. Now you interpret these. You interpret these guys as rewriting rules. Okay, that is, each time you are going to see x1, x2, you rewrite it as x2, x1. Each time that you see x3, x1, you rewrite it as x1, x3. And each time that you see x3, x2, you rewrite it as x2, x3. And this is a decreasing map, right? Generators, relations that live in arity in weight 2. What about the first problem arises when you take words with 3 letters. Now when you have words with 3 letters, there is something that can happen, is that you can have an ambiguity. So now you consider the critical monomials. I should not have given you the name first. So critical monomials, these are words with 3 letters, such that this and that, they are leading terms. Okay? Why? Because you can begin by rewriting this, or you can begin writing this. So you have an ambiguity. Okay, you want to go to Rome, and here you have 2 ways to go to Rome. So if you go, you take the left road or the right road. We have to solve these ambiguities. So we have nothing to do. And now step 4. You compute the graph, the diamond, associated to all the ambiguities. Oh, here there is just one critical monomial, which is x3, x2, x1. Okay? Now you rewrite you compute the graph associated to every critical monomial. In the example here, we have just one critical monomial, which is this one, right? So what can we do? We can first rewrite this. It becomes x2, x3, x1. Or we can rewrite that guy. It gives us x3, x1, x2. But, okay, we change the place of these two. And this guy is no more a leading term. Okay? But this is a leading term, so you can rewrite it. So you continue ad libitum. Oh, there is a leading term here. No leading term, no leading term. This is a dead end. But here, so this is no more a leading term, but oh, we appeared one new leading term. So we can rewrite this. Oh, but this is a leading term. And we are happy. From London to Rome, there were 2 ways, via Paris and Frankfurt, and they all lead to Rome. So that's okay. There is one terminal object. And when we have one terminal object for critical monomials, people call that confluent. There is a confluence property. Okay. So please step back. What does this mean? This means that you had relations. And then you're trying to check whether if you iterate the relations, you can find new relations. How can you write new relation? You start from one guy, you rewrite it, and then you rewrite it. And if you end with 2 different guys, you know that these 2 guys words with 3 letters, they are equal. So you have a new relation in arity 3. It is not the case here. This system is very coherent, and actually in this case the algebra is causal. So let me write the theorem, and then we can go to it. So here, there's no more relation. It's even much better than that. You will have your Poincaré-Birkowitz theorem here. Well, you see, huh? Anyway, what's the theorem? The theorem is, maybe I will cut it short and just say it's long to write it. If there exists a good or if there exists if there exists a totally ordered basis with a good order for all the monomials, good meaning the concatenation of words should be strictly increasing, such that all the critical monomials are confluent. So let me now just write this. So if there exists good order, if all the critical monomials are confluent, then, alors, the algebra A is causal. Well, this is what we were looking for, right? And then, of course, now, why did we do that if you really want to have bases of algebra, blah, blah, blah? Leading terms, there are guys that you do not want. You kill them, you rewrite them. So if you forget about all the leading terms in any words, then you get the basis of that algebra. So, words without leading terms, they form a basis for A, right? In other words, A as a vector space is isomorphic to the free algebra on V, where you kill all the leading terms. Right? So this is a monomial algebra. You kill monomials that you do not want. Okay? Right. Sure. So in other, well, that's exactly what I wanted to say. And then the proof, I won't do it. So, I mean, you've seen that before, right? What are we computing? We are computing a quadratic Grobner basis for the algebra, and the proof is that. So the proof is actually relies on the diamond lemma. So this is exactly Grobner basis and diamond lemma. Okay. So I hope nobody will erase the board during the lunch.
Please leave.
What?
Use that, please.
Yeah. No. No, this you should not have them. No, I would do. Yeah. So just I wanted to say, this afternoon I will do that for operads. I will tell you how to extend that for operads, and then we will see the properties of homotopy algebras, and we'll use these two books.
Please go away.
Do you have any questions? Yes.
The last one.
The last isomorphism, what's that? You want a basis for A. I claim that you can take any words in this basis, the free algebra, and you kill all the leading terms.
So it's another presentation.
It's not. Be careful.
It's another item.
No.
Is
No.
this a presentation of that one?
No. It cannot be a presentation of the algebra. This is not an isomorphism of algebra. It cannot. I killed by brute force. It's just as a vector space. You kill all the words which have these bits. You kill all the monomials which presents at least one of such. Why? Because you can write them. It's extremely coherent system. Pierre has a question. No.
No, it's okay. I'll ask you.
I have a question. This looks a bit like Pretty's original approach. Is it? I mean, there's the same thing about choosing carefully bases.
Previous, yes. It's indeed in PD. Previous, yes. Okay. Yes, exactly. It says if I have a basis of my algebra which behaves like that, then it is causal.
Yes.
And it's exactly, yes, it's exactly that. Yeah. Not written exactly with these words, but the underlying idea they are the same. Yes. You have a good. The idea is maybe you're reluctant. I was. Reluctant to sometimes consider bases or to put an order. No, guys, they exist by universal properties. Yes, but when you want to prove that their chain complexes are acyclic, sometimes it's good to take a certain order, to take this discrete mode theory or whatsoever. This is you take a vector flow whatsoever. This is the idea here. You have an algebra which does not need any basis. S of V, even when V is infinite dimensional, this is causal. You remember the causal complex last time. Yeah, but if you add a little bit of structure here, boom, then using the order spectral sequence, clock, you prove it's causal like this. And what is nice is, let me say something. You can develop causal-duality theory for inhomogeneous algebras. So, for instance, for the universal enveloping algebra of the algebra, and this gives you the PPW. It gives you a causal proof of the PPW theorem, which I like.
Can you have you ever tried this? Run this method on the Steenrod algebra to prove it's causal?
I personally didn't do it. I think that Pretty claims it works, as far as I remember.
Yeah, but it seems to me you've got a very systematic method.
Sure.
Rewriting method. I mean, do you think it's possible you could run that where you have to take some homogeneous sequence?
But you see again, each time we have an operad, Barkov-Bar resolution is a resolution. Can you give me more? Yes, here is a presentation of your operad. Oh, cool. Then I can simplify the resolution. Oh, but even more. The presentation comes equipped with a good basis, with a good order. Then you can make these choices and you have these homotopies for killing bar. The more you... Yeah, sure.
It sounds more like it because, of course, the Steenrod algebra has a good basis.
Sure.
Yeah.
From the order. That's right, yeah.
Yeah.
That's all it is.
It's squared. Is there any other question? Feel free. Don't ask me to do guest number again. Never ever. Okay, so let's see at 2 p.m.